All right, picture this. Your desk is just buried under a mountain of articles, research papers, notes, the topic. Something as crucial and complex as AI safety, and you need to distill the absolute most vital insights. Like right now, it's that familiar feeling, isn't it? Information overload. But this time, with the future of technology potentially on the line, that's really why we do these deep dives. Today, we're plunging into a truly, I think, groundbreaking research paper. It's titled "Out of Control: Why Alignment Needs Formal Control Theory and an Alignment Control Stack." Our mission today. To really unpack its core argument, which is that formal optimal control theory and this brand new framework they're calling the alignment control stack are absolutely essential for the future of AI alignment and safety. What makes this so intriguing right off the bat is how they're taking these, established engineering principles, things usually used for keeping complex physical systems stable, think rockets, power grids, that sort of thing, and applying them directly to the abstract, often kind of fuzzy challenge of making AI systems safe and aligned with human values. It's a surprising approach. Definitely offers a fresh perspective.
It really is. And it's not just about, tweaking algorithms here and there. It's suggesting a fundamental shift in how we think about controlling AI. Imagine moving from, let's build it and hope it works kind of mentality to a one where we can actually, mathematically, guarantee certain safety boundaries. That's the sort of paradigm shift control theory brings. It adds rigor. We can potentially move beyond just empirical observations and start building a more predictable, maybe even verifiable path forward.
Okay, so the paper starts by painting this picture of current AI alignment research, calls it a vast enterprise. And it is huge, right? Super multidisciplinary. You've got technical folks, engineering approaches, theoretical work, even socio-technical efforts trying to govern AI systems. Researchers are doing empirical evaluations. They're assessing how easily AIs might subvert safety protocols, developing adaptive deployment strategies for models you can't fully trust yet, and even digging into mechanistic interpretability, trying to understand the inner workings of these black boxes. But despite all this really incredible work, the paper says, look, there are two fundamental systematic gaps in how we're approaching AI alignment and control right now. They call them the formalization problem and the alignment coordination problem.
And these gaps, they argue, are precisely why the current state of AI alignment can feel a bit, out of control, as the title says. The formalization problem basically points out that a lot of current research, even the really technical stuff, is heavily empirical. It relies a lot on observing how specific models behave in specific tests, which is useful, of course, but it often lacks the kind of formal mathematical rigor you'd find in traditional control engineering. And this makes it incredibly difficult to generalize results from one AI system to another, or even to rigorously compare different safety techniques against each other.
Okay, I hear rigorous comparison, and sounds important, but I can imagine some listeners thinking, we're moving so fast with AI, who has time for all the heavy math? What's the real practical payoff here? What does that rigor give us that just watching the AI doesn't?
Well, what's really critical is that rigorous comparison, which formal methods enable, provides what the paper calls generalizable assurances. See, empirical observations can tell you if a specific AI model seems safe under the conditions you tested. Think of it like testing a car on one specific track on a sunny day. It might perform fine, but what happens if you change the car model slightly, or the training data, or the environment it's deployed in? Those observations might not hold. Formal methods, on the other hand, aim to derive mathematical proofs or guarantees of safety or alignment that hold across broader conditions, broader operational domains. This gives you predictive power. It helps you understand why a control works, not just that it seemed to work in one test case. You can actually quantify the uncertainty, establish safety bounds, maybe even guarantee stability under specific kinds of disturbances. And that becomes absolutely essential if you want to deploy these powerful frontier models reliably and safely in diverse, maybe even unknown, real-world situations.
That makes a lot of sense. The difference between testing one bridge versus having the engineering principles to know any bridge built that way will hold the load. And speaking of complex systems and missing blueprints, that brings us neatly to the paper's second big challenge, the alignment coordination problem. The paper points out that alignment isn't just one thing, right? It touches everything from theory to applied engineering to socio-technical stuff, but there's no clear, layered taxonomy, no agreed-upon blueprint for understanding where different controls are applied within the whole AI stack. From the actual silicon chips all the way up how AI impacts society. Because it's really tough to understand how these different control layers interact. How does a change down here affect something way up there? Or how do two controls at the same level work together or maybe against each other? It's like trying to fix a jumbo jet or manage the internet without any sort of diagram showing how all the parts connect and influence each other. You're kind of fumbling in the dark.
Exactly. And without that blueprint, that structured view, you're not just missing how individual controls work, you're missing the interaction effects. And those interactions are often where the most surprising and potentially dangerous behaviors can emerge. This lack of coordination means safety efforts in one area could be accidentally undermined by something happening in another layer. It makes achieving robust end-to-end safety incredibly difficult.
Okay, so given these, pretty significant gaps they've identified, the paper doesn't just point fingers. It proposes a compelling two-part solution. First, applying formal control theory to tackle that formalization problem, get more rigorous. And second, introducing this new framework, the Alignment Control Stack, or ACS, to solve the coordination problem, get a blueprint. Let's talk about control theory first. How do they define it?
They define formal control theory as essentially a powerful mathematical toolkit. It's been developed over decades, mainly in engineering, for analyzing and ensuring the safe and predictable behavior of complex dynamic systems. It includes a whole suite of concepts: system modeling, controller synthesis, which is designing the control stability analysis, robust control for handling uncertainty, reachability analysis to see what states a system can reach, and even game theory for analyzing situations with multiple agents, potentially adversarial ones.
And you mentioned formal guarantees earlier. That sounds promising. What kind of guarantees can we realistically hope for when applying this to something as messy as AI?
Right, formal guarantees. It's a strong term. What we're aiming for are mathematical proofs, or perhaps more realistically for complex AI, strong mathematical assurances that a system will behave within certain specified bounds or achieve a desired level of performance even when things are uncertain or disturbed. So, for instance, stability analysis and control theory, think about designing a car suspension. You don't want it bouncing wildly out of control after hitting a small bump. In AI, stability might mean ensuring the system's outputs or internal states remain predictable. They don't suddenly diverge into undesirable behavior patterns. Robust control is like building a bridge designed to withstand not just normal traffic, but also strong winds, maybe even earthquakes. For AI, it means designing systems that perform safely and reliably, even if the inputs are noisy, or the environment changes unexpectedly, which is crucial for the real world. Reachability analysis could help determine if an AI system could ever enter a state we've defined as unsafe, like generating harmful content or taking a dangerous action. And game theory gives us frameworks to analyze and design interactions between multiple AIs, or AIs and humans, to encourage cooperation or prevent harmful outcomes, even if some agents are trying to game the system. These aren't just probabilities based on past observations. They aim to be stronger, more rigorous assurances, often with provable bounds on performance or safety.
That really does sound like a step up from just, hoping for the best. Okay, so we have this conceptual toolkit from control theory. How does the paper propose we actually organize this huge task of aligning AI using these tools? Where does everything fit?
That's exactly where the Alignment Control Stack, the ACS, comes into play. The paper introduces it as this novel, hierarchical framework. It essentially decomposes an AI system's entire lifecycle and its operational environment into 10 distinct layers. 10 layers. And the really crucial point is that each of these layers provides specific opportunities for both measurement, understanding what's happening, and control influencing what happens. It's the blueprint we were missing. It provides structure. It's a comprehensive view, recognizing that control isn't just about the core algorithms. It's about everything from the physical hardware all the way up to public policy and societal impact.
10 layers is a lot to take in. Let's maybe dive into a few representative examples to give listeners a concrete feel for this stack's breadth. So way down at the bottom, a low layer. You got things like layer 1, physical infrastructure, or layer 2, system software. We're talking about what? Thermal management, workload scheduling, even the voltage settings on the chips. Or maybe layer 2, things like resource quotas, sandboxing provided by the operating system. So we're really talking control right down to the silicon level.
Absolutely. The paper makes the point that the reliability and performance of the physical infrastructure directly underpin everything else. If you have, say, hardware errors causing bit flips or thermal issues throttling performance unexpectedly, those problems can propagate upwards. They could corrupt data, affect model computations, or lead to unpredictable failures at higher levels. Controls here are often preventative things like robust hardware design, error correction codes in memory, maybe redundant power supplies. It's about ensuring that the very foundation the AI runs on is stable, secure, and reliable from the ground up.
And then moving up into the mid layers, let's say layer 5. Training process, or layer 6, behavioral output. Layer 5 seems critical. It covers things like validating the training data, detecting errors in that pipeline, designing the objective function itself, like what exactly are we telling the AI to learn? And then layer 6 is about what the AI actually does. It's observable actions, things like filtering outputs, detecting anomalies in behavior. This raises a key question for me. How does controlling the training process way back at layer 5 actually help prevent problems that only show up later as surprising or unwanted behaviors at layer 6 or even higher?
That's a great question, because layer 5, the training process, is fundamentally where the AI's core capabilities, its biases, its tendencies are actually formed. So it's a massively important control point. For example, by controlling data validation rigorously at layer 5, you prevent the model from learning harmful patterns from biased, corrupted, or malicious data in the first place. Garbage in, garbage out. Right. If you train an AI on a data set filled with toxic language, guess what? It's likely to generate toxic language. And carefully designing the objective function at layer 5 is maybe the most direct way we have to shape what the AI ultimately optimizes for. This has a huge impact on its behavior. If that objective function is poorly specified, even slightly ambiguous, the AI might engage in specification gaming. That's where it finds clever loopholes to maximize the objective score, but in ways we didn't intend, often violating the spirit of the task, like a robot cleaning a room by just shoving everything into a closet. It met the objective, but not how we wanted. Formal control methods can help design these objectives with greater precision, maybe incorporating safety constraints directly, and controlling other training elements like learning rates, regularization techniques, optimization algorithms. These help ensure the learning process itself is stable, converges well, and doesn't just randomly stumble into producing unexpected or misaligned behaviors later on during deployment.
Right, that makes sense. You're shaping the foundation of its behavior. And then layer 6 is where the rubber meets the road, what it actually does.
Right.
Okay, and then way up at the high layers, you mentioned things like layer 8, preference and reward, or layer 10, societal impact. This sounds like where the purely technical controls start merging with more human-centric governance, right? We're talking about techniques like reinforcement learning from human feedback, RLHF, where humans guide the AI's learning. Or red teaming, where you actively try to make the system fail safely. And even things like legislation, ethical guidelines, societal impact assessments at layer 10. This seems like where the code hits the real world, connecting AI to human values and society. How does the paper bridge that gap?
It really is where the technical meets the socio-technical. Layer 8, preference and reward, is all about mechanism design and incentive architectures. The goal here is to align the AI's internal reward signals, what it thinks is good, with actual human preferences and values. This is where RLHF fits in, but also things like constitutional AI, where you provide guiding principles. Think of it as trying to teach the AI not just what action gets a numerical reward, but what aligns with broader human ethics or intentions. It's about value alignment. Then layer 10, societal impact, is the broadest layer. It covers everything from public policy and laws governing AI use, to economic incentives shaping development, to international agreements, to how we manage the flow of information in an AI-influenced world. These high-level controls are often directive-setting rules and preventative at a macro scale. They aim to influence the entire ecosystem of AI development and deployment towards beneficial outcomes. And the ACS framework emphasizes that you need controls operating across all these layers. And importantly, it shows how controls can serve different functions. Some are preventive, stop bad things, some detective, spot bad things, some corrective, fix bad things, and some directive, guide towards good things. They all need to work together.
This whole stack-based approach really throws the importance of interoperability into sharp relief, doesn't it? It forces you to think about how controls at different layers interact, and, crucially, how they might accidentally interfere with each other. And the paper argues that formal control theory, with its shared mathematical language, gives us a way to actually analyze and understand these dependencies across layers.
Precisely. That's a key benefit. Without this kind of structured, formal perspective, trying to just layer on various alignment techniques, a bit of RLHF here, some red teaming there, maybe a content filter, risks becoming very ad hoc, you could end up with unpredictable emergent consequences where one control cancels out another, or they interact in unexpected ways, and you lack those generalized safety assurances we talked about. It's like trying to conduct an orchestra where every musician is playing from a slightly different score, maybe in a different key. It's just not going to be harmonious or predictable.
The paper breaks down this interaction analysis into two types: vertical and horizontal integration. Let's start with vertical. Vertical integration describes how actions or issues at lower layers propagate upwards and how feedback needs to flow downwards. For example, they mention how stochasticity, basically randomness in the training process down at layer 5, can directly affect the final model weights and therefore the behavioral output you see at layer 6. And it works the other way too.
If you discover a major misaligned objective way up high, maybe AI-generated misinformation is causing societal harm at layer 10. That feedback needs to flow all the way back down. Maybe you need to change the training data at layer 5, or adjust a reward model at layer 8, or even rethink the model architecture at layer 4. The paper even mentions specific control methods like linear quadratic Gaussian control, LQG, which sounds very engineering-y, showing how it can be used to mathematically model and co-optimize these interactions between different layers.
Yeah, and connecting this to the bigger picture, it really means that a problem observed at the societal level, let's say, an AI system consistently exhibiting biased behavior in loan applications, layer 10 issue, might require a solution that isn't just a patch at the output, layer 6. The root cause might be biased data used in training, layer 5, or even something subtle in the optimization process, layer 5, or model architecture, layer 4. You need a formal way to trace those dependencies and ensure that corrections made at one layer propagate effectively and predictably through the entire stack to address the actual root cause at another layer. This holistic system-wide view is exactly what formal control theory is designed to provide. It helps manage these complex chains of cause and effect across the hierarchy.
Okay, that's vertical. And there's horizontal integration. What's that about? This sounds like the interplay of different control mechanisms within a single layer, or maybe between parallel AI systems. For example, within layer 8, preference and reward, the paper notes that reward modeling, red teaming, and maybe using constitutional AI principles, these aren't separate solutions. They all need to work together in concert within that layer. Or maybe at layer 9, which deals with multi-agent systems. You might have communication protocols, incentive structures, and normative controls, all needing to be integrated horizontally to shape how multiple AIs behave collectively. So it's not just about what's inside one AI, but how multiple AIs, or maybe an AI and humans, interact and coordinate, like a team.
Exactly right. Horizontal alignment really pushes us beyond thinking about just single-agent optimization, which has dominated a lot of AI research. It forces us to analyze and design interactions within a layer or between multiple interacting systems, AIs interacting with other AIs, or AIs interacting with humans. This is a domain where dynamic game theory becomes absolutely essential. It provides the mathematical tools to model these strategic interactions. It allows us to design mechanisms like rules of engagement, incentive structures, communication protocols that shape collective behavior. The goal is to ensure robustly beneficial outcomes even when you have multiple independent agents, possibly with conflicting goals, maybe even some trying to deceive or collude. How do you ensure the overall system remains safe and aligned? That's horizontal integration.
Okay, this all sounds very comprehensive, very ambitious, but I can almost hear the skeptics tuning in right now. The paper anticipates some common counterarguments to applying formal control theory to AI, which seems wise. One really big one is just the sheer complexity and intractability. Modern AI systems, especially foundation models, are incredibly complex, right? High-dimensional, non-linear, they have all these emergent behaviors that seem to defy simple modeling. Surely you can't just slap traditional engineering math onto something so chaotic.
It's a very fair point, and probably the most common one. AI systems are incredibly complex, but the paper argues that formal control theory isn't just for simple, perfectly specified systems. In fact, much of modern control theory was developed precisely to handle uncertainty and complexity. Techniques like stochastic optimal control and robust control, for example, are explicitly designed for systems with randomness, noise, and high dimensionality. They often work with approximate or simplified models, but can still provide valuable insights, performance bounds, and safety guarantees, even when the true system is more complex. Think hierarchical control, where you manage complexity layer by layer. And areas like multi-agent control are specifically developed to analyze and manage systems with many interacting parts, where emergent collective behaviors are the norm. The goal often isn't to find the absolute perfect, optimal control law, which might be computationally impossible. It's about finding principled, robust strategies that achieve acceptable performance and safety within realistic computational constraints, even with imperfect models.
Okay, another critique you sometimes hear is about mechanistic interpretability. Some researchers argue that the real path to safety is through truly understanding the internal circuits or mechanisms of AI systems. A white box approach. If we can just understand how the model works internally, why do we need this external control theory framework? Why not just fix the internals directly?
The paper actually frames mechanistic interpretability as highly complementary, not as an alternative. It's not an either-or situation. In fact, interpretability is explicitly integrated into the framework, specifically within Layer 7 model internals. The idea is that control theory provides the mathematical tools and frameworks for using the insights gained from interpretability to design verifiable interventions. So interpretability helps you understand what's going on inside the black box. Maybe you identify a specific circuit responsible for a harmful bias. Control theory then provides the methods to design a control strategy, maybe adjusting parameters, adding constraints, modifying the training to mitigate that identified issue in a mathematically rigorous and predictable way. They really strengthen each other. Understanding enables better control, and control frameworks help translate understanding into action.
Right. Then there's the classic challenge, Goodhart's law. The idea that when a measure becomes a target, it ceases to be a good measure in quota. Critics argue that formal control relies on precisely specifying objectives or constraints, but trying to formalize complex human values almost inevitably leads to specification gaming, where the AI finds clever, unintended ways to meet the letter of the rule while violating its spirit. Aren't we just setting ourselves up for AIs finding loopholes in our carefully designed formal controls?
This is a really deep and valid critique, and the paper acknowledges it directly. Goodhart's law, specification gaming, these are fundamental challenges for any approach that involves optimizing an objective function, not just formal control. However, the argument is that control theory, particularly robust control in game theory, actually offers tools specifically designed to deal with model uncertainty and potentially adversarial behavior, which includes specification gaming. Techniques like minimax optimization, for example, try to find strategies that work well even in the worst-case scenario allowed by the model's uncertainty. Game theoretic formulations can explicitly model the AI as potentially trying to game the objective, and then design controls that are robust to such behavior. So you're not just naively writing down an objective and hoping the AI plays nice, you're trying to anticipate and proactively defend against potential misinterpretations or exploitation of the formal specification itself, baking that potential into the control design. It's about designing for robustness against gaming.
Okay, and one final counter-argument. Many practitioners, especially in industry, favor more empirical, iterative approaches. They argue we should learn through rapid experimentation, using human feedback, deploying models cautiously, and adapting based on real-world performance, especially given the cost and complexity of frontier models. Why complicate things with all this heavy, formal theory when an agile, empirical approach seems more practical?
The paper definitely doesn't dismiss empirical approaches. In fact, it argues they are essential. The point isn't to replace empirical work, but to ground it within a more principled, formal framework. Control theory itself includes many techniques for adaptation and learning, like adaptive control and, yes, reinforcement learning. These are already used. The goal proposed by the paper is principled adaptation, guided by theory, rather than purely ad hoc trial and error. Formal methods can help structure the experiments, provide theoretical bounds on uncertainty even when perfect models are unavailable, and help ensure that the adaptations being made are actually moving the system towards safety and alignment in a stable way. So it's about using the formal framework to intelligently inform the empirical process, understand its limitations, and potentially gain stronger assurances than empiricism alone can provide. It guides the experiments rather than replacing them.
Okay, so let's try to wrap up our deep dive into this out-of-control paper. The core argument, as we've discussed, is that formal optimal control theory, combined with this new alignment control stat framework, is really crucial for tackling two major challenges in AI alignment today. First, the formalization problem, making alignment research more rigorous, more comparable, more like a mature engineering discipline. And second, the coordination problem, providing that missing blueprint to integrate and understand how all the different alignment techniques interact across the entire AI stack, from hardware to society.
Exactly. And it's important to reiterate, this isn't about throwing out all the valuable empirical work, the interpretability research, the RLHF, the red teaming that's happening right now. It's really about augmenting those methods, grounding them within a more rigorous, verifiable, and holistic framework, giving them a common language and structure. It's essentially a call for the field to build out the theoretical and engineering foundations needed for reliable AI safety. This includes future research to develop tractable, formal models of AI agent dynamics, which is hard, applying sophisticated tools like stochastic optimal control and dynamic game theory to model complex AI-human and AI-AI interactions, especially concerning things like deception or collusion, and designing and critically verifying interoperable control protocols across the stack, ideally with provable guarantees about safety or alignment.
And of course, bridging that persistent gap between these elegant theoretical guarantees from control theory and practical scalable implementations that actually work for the massive complex frontier models we're seeing deployed today. That's a huge engineering challenge in itself. But the paper really suggests that to truly bring AI safely under control, we need to build this deep engineering discipline. We need to understand, predict, and mitigate these potential cascading effects across all its intricate layers. So it leaves us with a pretty profound thought, I think. If we can actually develop the methods to control AI down to its deepest layers and truly understand how those layers interact, does that give us a new kind of power, a new level of predictability? And if so, does that also place an even greater responsibility on us as developers and as a society in how we shape our future with this technology?
That's the crux of it, isn't it? And maybe a question for you, the listener, to ponder. What stands out to you most about this idea of AI potentially being out of control, and how this paper proposes using the rigor of control theory and a structured stack to try and bring it back within a more verifiable, predictable framework? It certainly gives us a lot to think about.